All right, this is a big topic. We're going to just go over what derivatives tell us. We're going to talk about first derivatives and second derivatives and try and interpret everything that we can there. We're going to build up a couple of tests as we go. So I'm going to cut this into two parts. So in just this first video, just so that it doesn't get like terribly long, we're going to focus specifically on using that last result that we proved from the mean value theorem, where we can use the first derivative to find where a function is going to be increasing and decreasing. We're going to extend that into something called the first derivative test, which is on your green sheets if you're in the normal face-to-face classes. So we'll kind of cover out how that goes. And then we will also talk about how to find absolute extrema on any interval. Right now, we have the extreme value theorem that helps us find it for functions that are continuous on closed intervals. But we'll extend that a little bit and say, well, what happens if we maybe don't have a closed interval? Anyways, let's get this going. So here's our definition of what it means for a function to be increasing and decreasing. This is an algebra definition or something that you maybe saw in an algebra class. Maybe I should say it that way instead. Notice the main thing that I mean here is that there's no calculus involved. If we've got a function defined on an interval, we'll say that the function is increasing on the interval if for every pair of x values that you get in that interval, whenever you've got x2 being bigger than x1, f of x2 is bigger than f of x1. So basically, look at a pair of x values, any pair of x values. If as you move from left to right, your y values get bigger, your function is increasing. The only difference for decreasing is that we switch up our inequality sign. So again, no real calculus statements involved here. So what we're going to do is grab that result from last time. That said, if we have a function that's continuous and differentiable on some interval I, then we can look at the derivative. If the derivative is positive on the whole interval, for all the x values on the interval, then we say that our function is going to be increasing. And if our derivative is negative, you can think that means the slopes are negative everywhere, and so then your function is going to be decreasing. Notice that really quickly, the order is really important here. This does not say that if f is increasing on the interval, the derivative is positive everywhere. This does not say that if f is decreasing on the interval, the derivative is negative on that interval. But if the derivative is positive on the interval, then your function has to be increasing. If the derivative is negative on the interval, then your function has to be decreasing. We'll probably, hopefully, look at a really quick example of why that might be the case. Let's just do it right now, actually. I don't want to get too far. So here's a really easy example to clarify what I mean here. Let's take a look at x cubed. This is what the x cubed function looks like, or at least approximately like this. What we'll notice is that this function is increasing everywhere. Increasing on negative infinity to infinity. There's like one weird spot right in the middle that we'll look at. But the main thing is that if you take a look at any pair of x values on here, you will always find that for a bigger x value, you'll get a bigger y value. That's the main thing. This is increasing everywhere. Now, what we will notice is that the derivative of this is 3x squared, and it is positive almost everywhere. F prime of x is positive on negative infinity to 0 and 0 up to infinity, because when x equals 0, f prime of x equals 0. We have that critical point, a horizontal tangent line. Now, what we found is that our function, if we looked at this, we said, oh, look, the derivative is going to be positive. If you put in negative numbers, it's going to be positive. If you put in positive numbers, that means that for this interval and this interval, we're guaranteed that our function is increasing. But we actually would say that it's increasing on the interval from negative infinity to infinity. So we're just going to have to kind of clarify some of this a little bit. No big deal. We'll just try and keep our heads about us. So how do we actually use the result? What we're going to do is recall the intermediate value theorem. The intermediate value theorem is the one that says you can only get from one side to the other by crossing through a line in the middle. So if you're a continuous function and you want to get from one side of a line to the other side of a line, you have to cross through the line. What we're going to do is say our line is at the x-axis. So let me redraw this. So let's say this is our x-axis. And let's say we find a point right here where something touches the x-axis. And maybe we find another point right here where that something touches the x-axis. And maybe we find a spot here where, I don't want to say there's an asymptote here, but I'm just going to say whatever we're considering doesn't exist. The only possible points that we can cross from one side of the x-axis to the other are at these three locations. The only way that we can go from positive to negative or from negative to positive is if we cross through 0, or we have some sort of a discontinuity. Maybe it doesn't exist for a second. There we go. And then maybe we cross through 0 again. So this is a fine version of this. The intermediate value theorem says as long as we're continuous, here's our spot where it's not continuous, the only way to cross from positive to negative is through the line in the middle, which is at 0. Notice that if we're talking about the derivative, these points where our derivative is equal to 0 or doesn't exist, those are critical points. So what the intermediate value theorem is going to tell us is that f prime can only change sign at, maybe I'll say, I don't want to say at points, I'll show you why, when f prime of x is equal to 0 or f prime of x doesn't exist. Now, I don't want to say critical points here because technically our function may not exist here either, in which case it's not a critical point. Remember, we needed the point to actually be in the domain of the function for it to be critical, but we'd still say that our derivative can change sign. So the derivative can only change sign at these spots. Notice that critical points are spots where the derivative is equal to 0, and some of the spots where the derivative doesn't exist, as long as they're in the domain. So we're going to basically be looking for critical points or spots where the derivative doesn't exist for other reasons, and we'll use the intermediate value theorem to set some stuff up. So let's look at this example. This is that function that we did, not in the last video about the mean value theorem, but in the one before that, I think we were finding absolute maxes and absolute minimums on like a closed interval from -2 to 4, something like that. But who cares? We're just going to find the intervals where this function is increasing or decreasing. If you want, you can go back to your notes to find the derivative. I'm not going to redo it. I'll just write up what we got. I've got it right beside me here. That's a minus sign. There we go. Over 3x to the 1/3. So this was our derivative. And so you'll remember that we found some critical points. The critical numbers were at 3, 3/4, and 0. 3 and 3/4 because those were the spots where the derivative was equal to 0, and 0 because the derivative didn't exist. We divide by 0. Now remember, this is in our domain, and so we called it a critical point. But even if it wasn't, we'd keep an eye on it because it still could be a spot where our derivative changes sign. So if we want to find the intervals where g is increasing or decreasing, what we know is that the only spots that it can change sign are at these x values, at 0, 3/4, and 3. What I'm going to do is create something called a sign chart that we're essentially just going to look at the sign. Maybe I'll give myself a bit more room. We're going to look at the sign on all the intervals in between. So what we're really going to do, let me draw a line here to just kind of cut this off. All right, there we go. What we're really going to do then is take a look at these intervals of x values from -infinity up to 0. Then we're going to look from 0 up to 3/4. And we've got our 3/4 in between. And then we're going to look at 3/4 up to 3. And then we've got our x value of 3. And then we'll look at 3 up to infinity. So we're going to kind of create this little chart here with intervals and points. And the points that we found are the ones where the derivative was either equal to 0 or didn't exist. And so what we're going to do is find the sign of the derivatives on all of these intervals. And maybe here I'll just give myself a reminder of like why I'm doing this. So my derivative doesn't exist here. My derivative is equal to 0 here and here. All right, so anyways, now what I want to do is I just want to check the sign of my first derivative. Now, you can do this pretty easily, I think, by just thinking about values between negative infinity and 0. These are just negative values. And what happens if you put negative values into this derivative? We're going to do a sign argument. We've done this kind of thing before. What you're going to notice is that for this one, g prime is going to end up having this kind of positive 2 times a negative number minus 3. Well, that's going to be negative. Sorry, let me do this. A positive 2 times a negative. And then we have this 4x minus 3. If x is negative, then 4x is negative. And if you subtract 3, that's more negative. And then the cube root of something is going to be negative here. So we have a positive times a positive over a negative. The sign of this thing is negative. Now you can look at the ones, the x values between 0 and 3/4. Essentially, you can say small x values. And so you're going to notice that the numerator is going to have this 2. That's positive. I'm just going to leave the sign off because it's not going to change anything. Then if you have that small number minus 3, that's going to be negative. Notice that if you have that small number in here, this is going to be small. And when you subtract 3, that's going to be negative again. But now your denominator switches signs. It's positive. So now you've got a positive over a positive. The sign of your first derivative is positive. You can do the same thing for x values bigger than 3/4. Suddenly, you're going to notice that you've got a negative still on that first factor. But this one, you're going to notice that if you have something bigger than 3/4, then suddenly this thing becomes relatively big-ish. And then when you subtract 3, it's still going to be positive. And the denominator is still positive because we have a cube root of a positive number. So look at that. This sign is negative. And then lastly, we've got x values bigger than 3. You can notice you're going to get positive and positive. Oops, I erased on accident. All over a positive. And so the sign here is going to be positive. So the way that I like to do things is just write down these signs. And then underneath, I'll just try and interpret what that means about my function. Now, we said this is an interval where the derivative is negative on that whole interval. We know that it's negative on this whole interval because the only spots that it could change sign were at 0, 3/4, and 3. So if the derivative was negative on some of that interval, it's negative on that whole interval, meaning your function is decreasing on that interval. And now suddenly on this interval from 0 to 3/4, our function is increasing. From 3/4 to 3, our derivative is negative, and so our function is decreasing. And then lastly, our derivative is positive, and so our function is increasing again. So normally, I'll end up just with something that looks kind of like this. I normally don't draw in all these lines because it gets kind of cluttery. Every now and then I will, and I'll show you why. But for now, this is what I'll have. And in fact, most of the time, oops, I erased the wrong stuff. Most of the time, I'll end up just having something that looks like this. What were my x values? 0, 3/4, and 3. So most of the time, I won't even write in the intervals. I can just kind of look and see. This is the interval from 0 up to 3/4. We'll string it all together. Cool. So if we're trying to answer this question, where are these things increasing and decreasing? And this is what will look like on an exam or a quiz or something like that. Maybe I'll have it written out like this where I'll label increasing and decreasing. We're going to say our increasing ones are these two. So that's from 0 up to 3/4 and from 3 to infinity. Oops, I almost wrote 3/4. There we go, from 3 to infinity. And our function was decreasing on these two intervals. That's from negative infinity up to 0, and from 3/4 to 3. So that's how we can answer that. I'm going to call this a sign chart because it's a chart that tells us the signs of a first derivative. And that's going to then lead us into giving us some interpretations of what the function is doing here. So that's how we can deal with this one. Now, again, this problem didn't go terribly long simply because we've already differentiated this and found critical points. But for some of these problems, it might take a little while to get through the first derivative, to find all the critical points, all the spots where your derivative could equal 0 or not exist, set up that sign chart and go. So here's the first derivative test. The first derivative test is a really, really helpful add-on to this. The first derivative test basically says that we know that local extrema have to occur at critical points. We also know that those critical points are the only possibilities. Now I should put a little asterisk here. Not really. The only possibilities where functions can switch between increasing and decreasing, because we just really care about the derivative equaling 0 or the derivative not existing. And for this one, what about problems in the domain? So that's the main thing. It doesn't have to be a critical point for the derivative to not exist, because maybe the function doesn't exist. But anyways, those two things, that's what I'm getting at. Those are the only possibilities of points where functions can switch between increasing and decreasing. So this is the important thing. These are the only points on our function where we can switch. Now, the first derivative test says that if you have a function that's continuous on an interval and you've got a critical point on that interval, and the function's differentiable on the interval around it, maybe not at c, because again, maybe the derivative doesn't exist. That's why it was a critical point. But basically, we'll say if the derivative changes sign from positive to negative, that means your function went from increasing to decreasing. And if you won't go from increasing to decreasing, maybe there was a local maximum there. Similarly, if you change sign from negative to positive, that means your function is changing sign, or changing from decreasing to increasing. Maybe it looks something like that. You've got that critical point here because the derivative doesn't exist. There's a local minimum there. And if the derivative doesn't change sign, then it's not a local extrema. This is what it looks like on that handout that we gave. The first derivative test, if you've got a function that's increasing and then decreasing, there's a local max here. I should probably do it like this. There we go. And similarly, if you go from decreasing to increasing, your first derivative goes from negative to positive, then there's a local minimum. Now, this is really important. This only happens at critical numbers or critical points. So a really classic case of this is if you had like a vertical asymptote on a function. Oh boy, let me redraw that. That's pretty terrible. You guys aren't safe from my bad drawings even though you're at home. All right, so let's say we've got a set of axes and we have some sort of vertical asymptote here. You might notice that you could have a function that goes like that and then like that. This is just a random bad drawing, but who cares? Notice your function decreases and then increases, but clearly there's not a local minimum here. So you need to have a critical number or a critical point. Because if it's not, if the function doesn't exist here, like a vertical asymptote where it's not in the domain, then you might get punked into looking like a local minimum. Notice the sign chart for this is going to look exactly the same. Negative first derivative, positive first derivative, decreasing, increasing. We don't want to get psyched out into thinking that that's actually a local minimum. So, got to be at critical numbers. So let's go back to this thing and let's find the local extrema. This shouldn't be too hard. Maybe I'll just jump right down to this. Actually, I'll rewrite it. G prime of x, we said, was 2 times x minus 3 times 4x minus 3. We had those critical numbers and we set up our sign chart. Looks something like this. And we said, I don't remember the signs. Let me go back and look. Negative. All right. We said the sign was negative, positive, negative, and then positive. And remember, I'm imagining the intervals around here. Since these things are all critical points, then we can apply the first derivative test to all of these. So what this really means is that our function, like we said, decreases and then increases. So that means right here, the first derivative test says that this is a local minimum at x equals 0. And then we said we were increasing and then decreasing. So bang, there's a local maximum right here at 3/4. And lastly, we go from decreasing to increasing. And so again, a local minimum right here. So these critical points now we can classify as local extrema in this case. So our local maximum was at 3/4. I'll have to find the y value for that in a sec. Our local minimum we said was at 0 and 3. And again, I'll find the y value. So let's go ahead and find these things. I think I already have them from when we did the absolute maxes and absolute mins. But let's just do it really quick. G of 0 is going to be 0 times 3 squared, so that's 0. So 0, 0 is a local minimum. G of 3 is going to be 3 to the 2/3 times 0 squared. That's 0, so this one's easy. And then G of 3/4, that one's going to be kind of annoying to find. That's 3/4 to the 2/3 times 3 minus 3/4 squared. 3/4 to the 2/3 is really 3/4 squared under a cube root. So that's going to be the cube root of 9 over 16. And then 3 minus 3/4 is really 2 1/4, but that's going to be 9/4, I think. Is that right? And then if we square that, that's going to be 81/16. So I think this is what we had before. 81 times the cube root of 9 over 16 times the cube root of 16, whatever that is. Or maybe I'll call it 81/16 times the cube root of 9/16. I have no idea what that y value is, but that's what it is. These are coordinates now. Now, if you wanted, we could go ahead and just plot these. And now we're able to plot local maximums and local minimums for this function, which is pretty cool. We haven't been able to do that before. One last note before we go. I'm already coming up to like 25 minutes on this video, and I don't want to make it too long. We want to talk about absolute extrema. So we have the extreme value theorem that says if your function's continuous on a closed interval, we know that there are both the absolute max and the absolute min on that interval. And we also know where to find them. They're at ending points or critical points. But let's suppose that we have a function that's continuous on just an interval. Could be open, it could be closed. Maybe it's a combination of both. And we have one local extrema occurring at some x value. So maybe we had a bunch of critical points, but only one of them was a local max or a local min. We could find that using this first derivative test now, right? Check the sign of the derivative around there. Let's say that we have one local extrema. What I want you to do is to go ahead and just plot that. So I'm going to get a critical point right here. I'm going to go ahead and make it one where the derivative is equal to 0, and I'll make mine a local max. Let's pretend I've got a local maximum here. And what I want to do is I want to draw out, extend this graph, but I want to see if I can not draw in another critical point. Meaning I want to not draw in another local maximum or local minimum. Or maybe I'll say instead of critical point, just a local maximum or local minimum. And what I want to do is see if I can not make this the absolute max. What I mean by that is see if I can get my graph above this line without doing this. I just drew in a local minimum here, right? So I want to see if I can get this graph to go above this dotted line, meaning this would not be the absolute maximum. We have some other absolute maximum here, without drawing another local max. Well, now I just did it again. Maybe I could do like a sharp corner, but then again, that's a local minimum. The only other way I could do it is to like make some sort of a discontinuity, but we said, nope, you have to have a continuous function. So what we're finding is that there's no way for this graph to get above this line if this really is the only local max or local min and our function's continuous. So if you've got a local maximum and it's the only one, there's exactly one on here, then it's an absolute max. And if it's a local minimum at that only one local extrema, then we know there's an absolute minimum. So this is a crazy question. Find the absolute extrema, if we can, of this function on this interval from 0 to infinity. Notice this is not a closed interval, so we cannot use the extreme value theorem to guarantee that both exist and to know exactly where they're going to be. So what we have to hope is that when we find the derivative of this function, and when we look for critical points, and when we look for absolute maxes and mins using the first derivative test, that we only get, or sorry, local maxes and mins using the first derivative test, we have to hope that we only get one of those things. And if we do only get one of those things, then we can say, well, that's the absolute extrema. So let's go ahead and do this. Let's find the derivative. You might not remember how to do it. This is not one that I would expect you to remember how to do right off the bat, but I'll just remind you. This is the one where we used logarithmic differentiation. Remember that? And so we ended up with natural log of y equals x natural log of x. And then you could do a whole bunch of work here to get y prime equals x to the x times 1 plus the natural log of x. And so if this is our first derivative, we can go ahead and find critical numbers by setting it equal to 0. You'll notice that this never equals 0. There's not any x value that we can put into this that will make it equal 0. It's also going to exist for this whole interval, which makes sense. It's the function itself that is the domain of that function. So for this one, you'll notice that the log isn't going to give us any problems because the interval we're looking at is 0 to infinity. We talked in a previous video about how any negative x values or 0 is a problem for logs. It's not going to be an issue here because of the interval that we have. But what we can do is set that equal to 0. So 1 over e is a positive number. It's in this interval. It's one that sets this derivative equal to 0, so it's a critical number. Critical number is e to the negative 1. There's only one of them. That's good news for us so far. What we're going to do is check it using the first derivative test to see if it's a local max or a local min. And then we can go ahead and make the extension to say, oh, it's going to be an absolute max or an absolute min. So here's our sign chart. Maybe I'll write it as 1 over e, just so you guys remember what that looks like. Go ahead and fill out your sign chart if you want. I'll put in the intervals here that you're really looking at, although I normally don't include these kinds of things. Normally I just kind of assume that that's what it is. So check the sign of the derivative. Remember, this is your derivative here on this interval. Check the sign of it on this interval and see what happens. Pause the video when you're finished with this example, or when you get stuck. Start it up again and see what happens. All right, I just wrote the derivative here just so we have something to keep looking at. What I'm going to notice is that all of these x values are positive, and so this piece here is going to be some positive number raised to a positive number. That whole thing is going to be positive. So I'm really not going to worry about that first piece. I really just care about the sign, of this part right here. So all I have to do is think about how logs work. And this is how logarithms work. For small x values, they're really, really, really negative. And for big x values, they're positive. So if you put a really, really, really small x value into here, it's going to be really, really, really negative. And then you have this 1 plus a really, really negative thing. That's going to be negative. If you put a really, really big x value in here, you're going to be going really far out on your log. It's going to be positive, plus 1, more positive. So that means your derivative is going to be positive here. If you're remembering, you might say, oh yeah, the derivative was equal to 0 at this spot. So maybe we'll just put that because it's interesting. Now we can say our function decreases and then increases, meaning what's going on here? A local minimum. So the first derivative test says there's a local minimum. Now, what we'll do is say, maybe I'll make my font a little bit bigger. One sec. Okay, so what we can say now is, since there's only one local critical point, it happens to be at, 1 over e. And it happened to be a local minimum, then we know that that local minimum is the location of the absolute minimum of f on this interval from 0 to infinity. So that's this main result that we have. We had a single, exactly one local extrema. We found it. It was right here at 1 over e. It happened to be a local minimum. Then we know that that has to also be an absolute minimum. So the absolute minimum is not 1 over e. It's actually f of 1 over e, which is x to the x. So that's 1 over e raised to the 1 over e. Or this is weird. If you want, you could think of this as like the eth root of 1 over e. Or, this is so bizarre, 1 over the eth root of e. I don't know what that number is. I have no idea. But whatever it is, that is the smallest y value on the graph of this function right here. Pretty cool. All right, we'll pick this back up in part 2, and we're going to talk a lot more about what the second derivative tells us.